start recording. And now we're ready to go, I think. Okay. So, number 3, we have a solid, we have a liquid, we have a gas. What's the 4th one we need to know this year? Not plasma. Aqueous. Do you remember the symbols that we use for each of these? Yes.
Bracket S.
Bracket S. Who's got the next one? Bracket L. You can either do an L like that or you can do an L like that. It doesn't matter. Okay? Gas.
Bracket G.
Bracket G.
Lower.
And how about aqueous? Bracket AQ. Now, I would like you to ask your partner if they know the difference between liquid and aqueous. And if you don't, that's fine, because we're going to talk about it today.
Aqueous is like solid, solving, and like liquid is like melting. Aqueous is like in water. Why are we always water? Why are we always gathered big parts of it?
Okay, let's take a look at this next page, because it takes a look at what the difference is between liquid and aqueous. So here we are starting with some solid table salt, and table salt is sodium chloride. Why is it ide?
Anion.
Because it's an anion, and the ending changes to ide. And you'll notice, does sodium change its name? No, because a cation does not change the name. Okay, so here we have sodium chloride, and it looks a lot like this. Silver, sodium, positive. Green, chloride, negative. Positive, negative, positive, negative. Sodium chloride, sodium chloride, sodium chloride. Positive, negative, alternating. Okay? So that's what we're seeing in this cube, is alternating positives and negatives. Sometimes that's a little hard to visualize because it's 3-dimensional, yes? So sometimes we simplify it by putting it into 2 dimensions. So we have the alternating chloride, sodium, chloride, sodium. And we know it's a solid because it's really organized. Yeah? It's tightly packed. It's very organized. Yes. Yeah, for sure.
No, like the.
Oh, like this part. No worries. I do. Just right there. You see it? It's like under some papers. You can feel free to take it out from under the papers. I won the messiest dust competition.
What?
The messiest dust competition. Ms. Riley and I, we were like explaining how this week has been like the week from hell, because we had like parent-teacher interviews last week, so we had to prepare for that. And then report cards are coming up, so we've been doing that. And we also have had long blocks this week, and we've also had to do our tech refresh. So we got a new computer, which sounds great, but you know, every time you get something new, you have to reinstall all the software that you don't have. And so, you know, everything has taken up way more time. And the less time I have, the worse my desk gets. And the less space I have, the worse it gets. And I needed to put out lab stuff. Yeah? So it's really bad right now. And Ms. Riley's like, oh no, mine's got to be worse. And I'm like, oh no, you know mine's worse. So Ms. Bellier judged, and mine was worse. Okay, so anyway, maybe Friday after school, that'll be my Friday afternoon relaxation, will be to clean my desk. Anywho, yeah. And that,
That's like when I sew.
right? And my house is like this right now too, because my whole brain is just full of doing report cards and marking quizzes and just like what I need to get done. And the whole cleaning thing has not happened and is driving me bananas. Anywho, let's look at what happens to get liquid. So this is liquid. NaCl. So we would write NaCl with a little L down below. And in order to melt it, because to go from NaCl solid to NaCl liquid, we have to melt it. How do you melt something? You have to heat it. So we heat it. Okay, so we heat it. And basically the little particles, they just start moving past one another. So instead of being locked in position, they can now move. Okay? And that's how we know it's a liquid, because the particles can move. Now, on the other hand, if we want to make it aqueous, instead of heating it, we are going to add what? Water. So we add water. So now instead of just having sodium and chloride, we also have, look at this, little water molecules everywhere. Yeah? So over here, we have pure NaCl. On this side, we have NaCl mixed with water. But those particles are still free to go zooming about. Whee! Off they go. Okay, they go all over the place. Okay, so this is aqueous. NaCl. So we would put an AQ at the end. And just like in the liquid, the particles can move. Yes. This is part of understanding how physical processes work. Yes? And it's part of understanding the difference between liquid and aqueous. So I might say, if I dissolve sodium chloride in water, what state does it become? Aqueous. If I say I melt some sodium chloride, what state does it become? You would say liquid, right? Because often people think, oh, I've dissolved it in water, it must have become a liquid. But it doesn't, it becomes aqueous. Yeah? So am I going to have you draw these pictures? No. But do I need you to understand that aqueous, like when you put it with water, that's not a liquid, it is aqueous. You don't have liquid sodium chloride, you have sodium chloride dissolved in water. So if we look at, here's just another couple representations. You can see that the particles in the sodium chloride liquid, they're just sort of jumbled all over the place. Yes, they're not organized anymore. They can move past one another. All right. And here we have water molecules, chloride ions, sodium ions. That's very nice. Okay. Now, what temperature do we need to be at to get liquid sodium chloride? 800 degrees. Are we going to do that in the lab? No, we are not. How about dissolving sodium chloride? Can we do that in the lab? Absolutely. And in fact, either tomorrow or Monday, I know I said our test was going to be Monday, but I think it's going to be on Tuesday instead because I'd like to get a little bit more lab done and before we do that. Yes. We have a long block on Thursday, Friday next week. It's because, don't even get me started. There's a whole thing behind it. But because of the Remembrance Day Assembly, they're long blocking.
Oh, yeah, yeah. Oh.
Okay?
I have information about that. They're calling down by room number.
It's very political. I can say nothing.
Wait, what happened? What's political?
I don't know. I don't know how it happened. I don't know why it happened.
Although.
The only thing I know about it is that whoever talked to me about it said, I don't want to throw anybody under the bus. And I'm like, okay, I don't need anybody thrown under the bus. Like, I'm like, why wasn't it a 5-period day? And I'm like, oh. Anyway, so we're good. We're good. We're just going to move on. Just move on. Moving on. Okay. Yeah, politics. I don't know what it is. I mean, I'm sure there were good reasons behind it. I don't know what they were. That's what it comes down to. I have no idea, and nobody seems to want to talk about it. And I'm like, okay, that's fine. Just, I won't ask any more questions, right? Yeah. Now, here we have a connection to a later unit. Our next, not our next unit, but one of our later units is going to be electricity. And when we have current electricity, what do you think of when you think of current? Current. Like water flowing, yes? Water flowing is current. Well, when we have electrical current, what do you think is flowing? Yeah. Electrons can be flowing. Any particles with a charge are flowing. Okay, so it's the flow of charged particles. So if you want to have a current, yes.
Does the current have negative charge in it or positive?
It can be either. So when it's in a wire, it's electrons that move. So it's the negative charges that are moving.
Okay.
But if you have a solution, right? You have the dissolved particles. If you were to put a negative plate over here and a positive plate over here, the negative particles would be attracted to the positive plate, so they would move this way. And the negative particles would be, oh, did I do that the wrong way? I did that the wrong way. Sorry, I'm drawing it backwards. Oh, and now it's doing crazy things. Getting used to my new pen. Sorry. Here we go. Sorry, negative would be attracted to the positive, so they would go that way. And then the positives would be attracted to the negative plate, so they would go that way. And it turns out that negative charge flowing one way and positive charge flowing the other way are the equivalent of each other. Okay? So when we get to the electricity unit, we'll talk about that more. But what you can see is that we have, in here, we have some charged particles. right? And what do we need for current electricity? We need charged particles. And if they're going to flow, what do they need to be able to do? They need to be able to move. So, if you need to have charged particles that can move, which of these three things can conduct electricity? Solid, sodium chloride, liquid, sodium chloride, or aqueous sodium chloride. Chat with your partner about that. Take a look at the pictures of the solid, of the liquid, and of the aqueous.
Who's cheating for this? I already know. It's not even that. It's not even that bad. Like, have you seen like tangent? You don't have to theta. You have to learn how to.
So if you look at those three highlighted things, the three green highlights, we have our solid sodium chloride. Can solid sodium chloride conduct electricity? Does solid sodium chloride have charged particles? Yes. Can they move? No. Therefore, can solid sodium chloride conduct electricity? No. How about liquid sodium chloride? Does it have charged particles? Yes. Can they move? Yes. Can liquid sodium chloride conduct electricity? Yes. Aqueous sodium chloride, does it have charged particles? Can they move? Can it conduct electricity? Yes. Okay. And later on, we'll learn that in a wire, the valence electrons, the electrons in the outer shell of metals, can actually flow from one atom to the other, but we'll do that later. Okay, so the ones that can conduct electricity, that would be yes to liquid, yes to aqueous, no to solid. Melting and dissolving, here we go. We're starting with solid, we add heat, and we go to liquid. What's that process called? That's called melting. Is that a chemical change or a physical change? Physical, how do you know? There's no new substance, right? It's still just sodium chloride. So we have a physical change. Okay, if we have solid sodium chloride and we add water, what is that process called? Dissolving. Do we have a new substance or is it just the same substance? Same substance, no new substance. So therefore, is it a chemical change or a physical change? Physical change.
I have no idea exactly why.
We start with salt, we finish with salt, it all tastes salty. The only thing you don't want to taste is liquid sodium chloride. Why do you not want to taste liquid sodium chloride? Because it is very hot. It's 800 degrees. Let's agree that we don't want to taste something that is 800 degrees. And now we are going to watch a little video.
When an ionic...
Okay. And now I think I need to plug this in.
substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens. When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogen.
The majority of us take for granted that certain things dissolve.
Three, two, one. Oh dear. Hey guys, I'm Nate. Welcome back to the backyard. Today we've got a fun experiment that we're going to try thanks to the suggestion of YouTube user Robert Vipperman. Robert wanted to know what would happen if we mixed molten salt with either liquid nitrogen or dry ice. Well, today is not the day for the liquid nitrogen test, but it is the day to see what happens if we pour molten salt onto dry ice. Well, we've got our foundry, we've got our salt, and we've got some dry ice. Let's try mixing them together. Now, as a first step, what we want to try and do is clean out our crucible. All of the crucibles we've got currently have residue from other projects in them. This one seems to have quite a bit of aluminum built up on the sides. So we're going to try and chip out what we can, then fire up the foundry and see if we can melt out the rest and shake it out so we have a mostly clean crucible to melt our salt in. we do want a small reservoir in our dry ice to pour the salt into so it doesn't just scatter all over the place. So let's take our drill bit and try and carve a hole down into the ice just a little bit. Ooh, that looks toasty. See how well molten salt pours out of a crucible. Huh. Well, it's cooled down. It certainly bubbled a good amount, but it didn't react horrendously violently at all, at least not yet. I guess it's still possible to get there, but even the salt that's just on our pavers has cooled down to being solid. Looks like our salt inside our dry ice has as well. Let's see if we can tip that out. There you go, a nice solid chunk of salt right there. I think the salt in our crucible is still liquid. Try pouring a little bit more in. Skimming some of this aluminum off the top. It's just melting more aluminum as it goes. Whew. I certainly wouldn't want to get that on me, but it's nowhere near the violent kind of reaction that we've seen in other people's channels where they pour salt into water. Ooh, the middle of that is still squishy. Definitely hasn't cooled down all the way. Very hot. Also very hot. Still both very hot. All right, now I know this is probably filled with aluminum and some other trace metals, but I'm gonna lick it. Surprise of all surprises, it's salty. All right, now this is finally cold. That one's a little less cold, but it's also
here's one of the biggest things that people don't understand in chemistry. Keep this in mind. When a liquid boils or evaporates to become a gas, the molecules don't come apart. So let's talk a little bit about liquids, evaporation, boiling, and molecules. So here is a very tiny glass of water. Well, it's a tiny glass of water that we've zoomed in zillions and zillions of times so we can see what makes it up. And what we see is that this glass of water is made of all of these water molecules. One oxygen atom connected to 2 hydrogen atoms. That's why we call it H2O. So our glass here contains lots of molecules of liquid water. Let's now make some steam, some gas water. What we're going to do is we're going to heat up this liquid water. And as we heat it up, the molecules in it are going to start moving faster and faster and faster until some of them are moving so fast that zoom, they can jump, shoom, right out of the liquid water, enter the air above that liquid, and start flying around. Now, these guys up here are molecules of steam, also known as gas water. So here's the main point. When they're liquid water, the molecules, H2O, are packed really close together. When they're gas water, or steam, they're still molecules of water, 1 oxygen and 2 hydrogens. It's just that now they're not as densely packed and they're flying around in the air above the liquid. Here is the mistake that so many people make and that I don't want you to make. This, as we said, is the way that water does evaporate. Here's the mistake that people make. Here is another glass of water. So many people think that when water molecules become gas, that they have to break apart, that the atoms that make up those molecules split apart from each other, and that's the only way that the liquid water can become gas or steam. So we have these molecules here, and they have to rip these atoms apart. And so that if we were to zoom in and look at steam, we wouldn't see water molecules, but we'd see all of these pieces of the molecules, all these atoms ripped apart. This is wrong. Here's the big red X. I don't want you to make that mistake. On the other hand, here is the right way that boiling or evaporation happens. The molecules look just the same in gas as they do in liquid. They do not, big red X, they do not split apart into the atoms that make them up. Same in liquid, same in gas. Okay, now this isn't just true for water. This is true for anything, for any liquid that can evaporate or boil to become a gas. So here I have a tiny amount of gasoline. The molecules look like this. 8 carbon atoms surrounded by 18 hydrogens, and then here I have some alcohol, a carbon with a bunch of hydrogens, and then an oxygen. Now, alcohol and gasoline can both evaporate. If you're like me, you love the smell of gasoline, which is like those vapors that you get when you're filling up your car. I love it. So you know firsthand that gasoline can evaporate and become a gas. Here's the point though. Here is the wrong way to think about evaporation. If a gasoline molecule looks like this, the wrong way to think about it is that these molecules would come apart into the pieces and into the individual atoms. And the same thing here with the alcohol. This is wrong. These molecules here have split apart into atoms and pieces of molecules. On the other hand, the right way to think about this is that both the alcohol and the gasoline molecules just nicely lift out of the liquid when they turn from liquid to gas. This is what the liquid would look like. The molecules are all tightly packed together, and here's what the gas would look like. The same molecules, they're just floating around in the air and they're further apart. So once again, don't make that mistake. Always remember that when a liquid boils or evaporates to become a gas, the molecules don't come apart.